Okay, so I want to give you a little bit of insight into why the harmonic oscillator is so important in describing quantum field theory, because it does play an important role. And to do this, we are going to do an experiment. Um, Not a real experiment. I don't have a lab. In fact, I'm forbidden from walking into any lab, but I'm still allowed to do thought experiments. I'm just going to think about doing an experiment. So let's imagine I go to my fictitious lab on Monday. I have a piece of equipment, sophisticated equipment. It's a box, and I can catch a particle inside that box. So here I have a particle. I've created that state, and I've got a very accurate way to measure the energy of that particle. I find it has an energy E1. Then tomorrow I go into my lab and I do a second experiment with the same box, okay? And I create a second particle, slightly different way. And this new particle has an energy E2, which differs from E1. Once I've done this, I can already make a prediction. And the prediction is as follows. I say, I should be able to produce another state inside my box. This state will be a two-particle state, and it will have an energy of E1 plus E2. So let's see why that's possible. Remember here, I said I want to study non-interacting particles. That's the simplest case I could possibly study. So let me start with the simple case and build up from there. If I've got non-interacting particles, then if I've got particle 1, it doesn't even know whether particle 2 is there or not. And if I've got particle 2, it doesn't even know if particle 1 is there or not. So if I can have particle 1 and I can have particle 2, then for sure I can have particle 1 and particle 2 together. Secondly, there's no energy of interaction between these two particles because they're not interacting. So to get the total energy, I just sum the two energies. And so that's why I would predict now that I get a state of E1 plus E2. So any Hamiltonian that I'm going to use to describe quantum field theory, it must have the property that its spectrum is additive. So if E1 is an energy level and E2 is an energy level, then E1 plus E2 must also be an energy level. How special is that property, that adding energy levels, we get another energy level in the system? Well, let's think of a few examples that we've solved. You may have remembered solving the problem for a particle in an infinite well. Okay, so what I've plotted here is V of x. This is x. The potential barrier is infinitely high, so the particle moves freely between the walls of the well, but it can't get out of the well. Well, in this situation, we know that the momentum of the particle from de Broglie is just h over its wavelength. Let's say that the well has a total width of L. So we know that the wavelength will just be some integer n over 2 times by L. So that's the form of the momentum. Because this is a free particle, the potential is flat, there's no forces. So because it's a free particle, we know that the energy is just p squared over 2m. And using the formula that we have for the momentum, this is going to be h squared n squared over 8ml squared. And this is the energy of the nth level. So if we look at this, E1 would be equal to h squared over 8ml squared. E2 would be equal to h squared over 8ml squared times 4. E3 would be equal to h squared 9 over 8 ml squared. Well, if you take E1 plus E1, this is going to give you 2h squared over 4ml squared. This is not in the spectrum. Here's another one. If you take E1 plus E2, in that case, you'll get 5h squared over 8ml squared. Again, it's not in the spectrum. So if you wanted to build a theory of quantum fields for which you know the spectrum must be additive, you would never try to build it on the Hamiltonian for a particle in an infinite well, because when I add energy levels for the particle in the infinite well, I simply don't get another allowed energy level in the spectrum. If you think about hydrogen, well, in the hydrogen atom, you know, the potential looks something like this. So the energy levels get much more closely spaced as you go up. And in fact, in this case, you might remember that the energy levels go like 1 over n squared. So you start off from some negative value, and you get closer and closer to 0, where you're no longer bound, but the energy levels go like 1 over n squared. But again, if you just take two arbitrary energy levels in hydrogen, that sum is not in the spectrum of the hydrogen atom. So you could never use the hydrogen atom to build a quantum field theory. In fact, there is only one system that has this property that if you add two of its energy levels, you again get an energy level inside the spectrum of the system. And that's the harmonic oscillator. So remember, for the harmonic oscillator, okay, I'm going to subtract off the ground state energy. In that case, the energy of the nth level is just n times by omega. So then En1 plus En2 would be N1 omega plus N2 omega. But this is N1 plus N2 omega. And that's just En1 plus N2. So for the harmonic oscillator, we see that the spectrum is additive. It's the only system with an additive spectrum. We need that property when we want to model particles. So you should, in general, always expect that any quantum field is an assembly of oscillators. If it's free particles, it's non-interacting oscillators. And if there are interactions, then those oscillators will be interacting. But as you switch those interactions off, you just get a free assembly of harmonic oscillators. Great. That brings us to the end of the ideas of this chapter. The last thing left to do is to give you a few hints for the exercises. We'll do that now.